All right, mathematicians, my sound is on this time. I mentioned last lecture that I recorded both lectures without sound. So, sorry, watching TikToks. So now we're on to section 2.2, which is about limits of a function and limit laws. So we often want to study a function's behavior around or near a specific point. Well, why not just plug in that point, right? Like if I want to know where the function is at that point, well, I should just plug it in. Well, we can't learn much from just one data point. If I plug it in, I only have one data point. I shouldn't just make some inferences off one source, right? You shouldn't. Well, sometimes I can't even plug into that point. So I have to talk about what's happening near that function, near that point, around of the function. So remember how we talked about last time f of x plus h minus f of x divided by h? I can't plug in h equals 0. So that's not the only time I can't plug in the number. Let's look at this example. So if we're given f of x equal to x squared minus 1 divided by x minus 1, that looks like this beautiful picture that I've drawn. And I have a hole at 1. I can't plug in 1 because I'm going to divide by 0. But I can simplify the function. So as you look down here, I can I can rewrite the numerator, x squared minus 1. This is what we call a difference of squares. There's also something called a difference of cubes. So the difference of squares, I can rewrite as x minus 1, x plus 1. X squared minus 1 equals x minus 1, x plus 1. And then the bottom is still going to be x1. Well, now I have an x1 on the top and the x1 on the bottom. As you can see, I crossed those out, leaving me with just x plus 1. But still, x can't equal 1. Well, I can compare it to this other function, g of x, who just equals x plus 1. It's the same exact graph, but now I don't have a hole at x equals 1. Now I can plug in x equals 1, I actually get 2 back out. So even though at 1, f of x doesn't exist, as I approach 1, my function is approaching 2. So as x approaches 1, f of x is approaching 2. So we say that the limit of f of x as x approaches c is L. And we write that as this limit, LIM, and then under it, x arrow c, f of x equal to L. So I would say the limit of f of x as x approaches 1 is 2 in this example above. Oh yeah, I wrote it right there. So if I give you an identity function, I don't want to show too much, which is just when f of x equals x, the limit of that, so the limit of f of x as x approaches c is equal to the limit, well, f of x just equals x, so I can put x in right here. So x approaches c equals, well, c. If I'm just a straight line and I'm approaching x, or sorry, if x is approaching c, what should x be? It should be c. So if f of x just equals some constant, a flat line, the limit of f of x as x approaches c is equal to the limit of c as x approaches c. Well, x doesn't have any influence on that. It's just going to equal c. So these are cases where the limit is always going to exist. But what about for every other function? Does the limit always exist? So let's consider the following 3 functions. And we're going to ask the question each time, what is the limit as x approaches 0 of f of x? So our first one is f of x equal to 0 when x is less than 0, and it's going to equal 1 when x is greater than 0. As you can see on the left hand, I'm going to be approaching 0. On the right hand, I'm going to be approaching 1. I can't have a limit equal two different numbers. It has to equal one number. So there's what we call a jump. A limit does not exist when there's a jump. Right? So that's one case. Our second case is f of x equal to 1 over x when x doesn't equal 0. And when x does equal 0, I just made my function equal 0. As we're approaching 0 on either side, one side I'm going up and up and up and up, and I'm never stopping. On the other side, I'm going down, 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 and again, I'm never stopping. F of x is going larger and larger, so towards infinity and negative infinity, but the function's not bounded. So again, even if they are going towards two different numbers, they're going off to really big numbers that don't ever actually exist because the function's not bounded. So again, the limit does not exist. So my third favorite one is f of x is equal to 0 when x is less than 0. So I have this flat line. And then when x is greater than 0, the function is going to equal sine of 1 divided by x. So I get this crazy oscillating function. That goes off like that. So as I'm approaching 0 from one side, it's just a flat line. As I'm approaching from the other side, my function is oscillating. It's bouncing between -1 and 1. I don't know. No, it's oscillating too much. I spelled the word much wrong. Good job, Mackenzie. So the limit doesn't exist. So we have three cases. If there's a jump, if my function's unbounded, so going off towards infinity, and if my function oscillates. And it's oscillating more and more the closer to 0 we're getting. So those are the three cases where a limit does not exist. So what about our limit laws? We've been having laws a lot lately, exponential and logarithms, and we also have some similar ones for limits. So let's first assume that L, M, C, and K are all real numbers. That's what I mean by element in this double bracket R. We're going to assume that the limit of f of x as x goes to c equals L, and the limit, I can write that a little nicer. Equals m. So notice that these two functions, different functions, but they're both going towards c. That's really crucial. They have to be both going towards the same thing. All right, so the sum rule. If I take the limit as x approaches c of f of x plus g of x, I can just add those limits together. So that's going to equal L plus m. The difference law says that I can subtract the functions. Well, then their limits are going to subtract. The constant multiple rule, I also like to call the coefficient rule. It says when the limit goes to as x approaches c of k times f of x, that's just going to equal k times the limit. Product rule, the limit of f of x times g of x as x goes to c is going to be L times m. The limit of each of those multiplied by each other. Quotient rule works the same way. The limit of f of x divided by g of x is x approaches c. It's going to be L divided by m. But this is only when m equals 0. Power rule says that the limit as x approaches c of f of x to the n is just going to be L to the n. In this case, n is a positive integer. Similarly, the root rule is the limit of the nth root of f of x as x approaches c is going to equal the nth root of L. Also can write that L to the 1 over n. So I might have sped through those a little fast. Pause now and write those all down, because you will use them a lot. So let's use them in an example. I ask you to find the limit as x approaches -2 of the function square root of 4x squared minus 3. I write that down below, and then the root rule says I can just bring the limit inside the root. Sum and difference rule says I can just find the limit of each of these terms. Well, I can then use the constant multiple rule and the power rule here to just see that I can plug in -2. And I know earlier that if it's a constant, I'm just going to be left with that constant. So that's how we get the square root of 4 times -2 squared minus 3. So that's going to equal the square root of 16 minus 3, which is then going to equal 13. All right, so combining sum and difference, constant multiple, and the power rule gives us this really useful theorem. It says that if p of x equal to an x to the n plus an minus 1, x to the n minus 1, so on, meaning that p of x is a polynomial, then the limit of p of x as x approaches c is just going to equal p of c. Meaning I can just plug in c into my polynomial and get my limit, instead of rummaging through each and every limit law that way. It makes our life a lot easier moving on. So I can also then combine this theorem and the quotient rule, and I can get this next theorem. So if p of x and q of x are polynomials, and q of c does not equal 0, then the limit of p of x divided by q of x as x approaches c is just going to equal p of c divided by q of c. This is really useful. A lot of limit problems you'll see are usually quotient ones. Alrighty, so we can use it on this example down here. The limit as x approaches -1 of the function x cubed plus 4x squared minus 3 divided by x squared plus 5. So we're going to use theorem 2.2.2. And I can just plug in c, in this case -1, into each x value in the numerator and the denominator. That's how I get -1 cubed plus 4 times -1 squared minus 3 over -1 squared plus 5. So that's going to equal -1 plus 4 minus 3 divided by 1 plus 5. So 0 divided by 6, which is just 0. Well, one problem that I didn't talk about where a limit doesn't exist is when we have 0 divided by 0, which usually means it's the indeterminate form. We'll get more into that later in the semester, but for now, let's talk about a really fun limit, one of my favorites. And we're going to ask, how can I find the limit for sine of x divided by x for x equals 0? So if I plug in 0 for x, I get sine of 0 divided by 0. Well, sine of 0 is 0. So I just get 0 divided by 0. That doesn't really work. So we can use something called the sandwich theorem, sometimes also called the squeeze theorem. So suppose that I have three functions, g of x, f of x, and h of x. And we're going to suppose that g of x is less than or equal to f of x, and f of x is less than or equal to h of x for all x on some interval containing c. So suppose the limit as x approaches c of g of x equals the limit as x approaches c of h of x, and that all just equals L. So my bottom function's limit and my top function's limit are equal to each other, and we called that limit L. Then my middle function, its limit as x approaches c is also going to equal L. They're all going to equal the same thing. That's called the sandwich theorem. If I sandwich f in between these two functions that have the same limit, f also has to have that same limit. So without proof, I'm just going to tell you that cosine of x is going to be less than sine of x divided by x, which is then again less than 1 over cosine on some small interval around 0. Okay? I'm not showing the proof of that right now. It's actually a really cool proof. If you want to look it up, there's lots of different ones. But this is probably the most common proof for the sandwich theorem. So I already know that g of x is going to be less than f of x less than h of x for all x on some interval. Now I need to make sure that the limit of cosine of x and the limit of 1 over cosine of x as x approaches 0 are the same. So let's do that. So the limit as x approaches 0 of cosine of x, that's just cosine of 0. So and that's just 1. Similarly, 1 over cosine, the limit as x approaches 0 is going to equal 1 over cosine of 0 equal to 1 divided by 1, which is 1. So perfect. My two pieces of bread, their limits equal to 1. So the limit of the peanut butter in the middle, I can say by sandwich theorem, the limit as x approaches 0 of sine of x divided by x is 1. So this is a really useful limit, and you will use it a lot in this chapter. Not only just the sandwich theorem. All right, so let's work on this example. This one's my favorite example. My students had it on a quiz last year. I hope that's a really good hint for you. So if we're given that the square root of 5 minus x squared is less than or equal to f of x, which is then less than or equal to the absolute value, square root of 5 minus x squared, this is our small interval. Remember how we were told that this holds true, this less than line holds true for all x on some interval. That's what this interval is. Don't get too hold up on it, okay? That's just our small interval that contains c. We're asked to find the limit as x approaches 0 of f of x. So I have that these three functions are less than each other, 1 by 1, on this small interval. So then I need to see that if each piece of bread limit equals each other. So I take the limit of the square root of 5 minus 2x squared as x approaches 0. I move the limit inside the square root. And then since I know that polynomial theorem, I can just plug in 0 right here to 5 minus 2x squared. And I can get 0, no, not 0, the square root of 5 minus 0. Well, that just equals the square root of 5. So I need to test my other piece of bread. So the limit of the square root of 5 minus x squared as x approaches 0 equals, similar to above, the square root of the limit of 5 minus x squared as x goes to 0. I can plug in 0 to that polynomial, and I'll get the square root of 5 minus 0 equal to the square root of 5. So then we can say by squeeze theorem or sandwich theorem, same thing, the limit of this unknown function as x goes to 0 is 5. So that's how we can use squeeze theorem. So I'm going to leave you guys here today. You have some homework that you need to do, maybe a quiz to study for. Let me know if you liked me reading through notes versus talking while I have notes already written. This might have been a more, like, I guess, well-composed lecture since I've done it like 2 or 3 times. So if you hate it, let me know. If you like it, let me know. All right, I will talk to you guys tomorrow.